Hey everybody, it's Mr. Ray here with our next calculus lesson. This would be lesson number 13 in the distance learning. We're going to be talking about the product rule today for derivatives. Just to give you a little heads up in terms of what's coming up. So we're going to do two more lessons this week. We're going to talk about the quotient rule and we're going to look at second derivatives. And that's kind of end of a section in terms of just derivatives, okay? We're actually going to be leaving out derivatives of exponential functions and derivatives of trig functions, and I'll also usually include derivatives of logs and ln functions too, but because of the time constraints, we're going to be leaving that out. And so starting next week, we're looking at curve sketching. So that's where we learn how to do a better job of sketching curves. Now, in this case, it's just going to be polynomials because since we're not doing derivatives of other types of functions, it doesn't make sense to do curves of those or sketches of those functions. So it'll probably be 2 to 3 weeks. Looks like from the guide I have, it looks like 6 lessons on that. So that looks like 2 weeks. And at the end of that, so 1 more week of derivatives, 2 weeks of curve sketching, and probably a week last week, or depending on where we are, would be on optimization. Okay, so that's an interesting thing. Some longer, more complicated questions to wrap up the course. Okay, I'll put a note on let you guys know separately for those of you who don't listen to the lessons. We are not going to be doing a summative in the course. So that means no final exam and no big assignment at the end. So basically your mark will be based on, well, what you had up to midterm, plus the assignments, weekly assignments up till the end of the course, okay? And that is a course-specific thing. So the calculus teachers have decided that. What you might find in your other courses depends on those teachers. It has to be um, the same summative decision for all the sections of the course. So if you're taking an English course, well, all the grade 12 English course teachers would have to decide this is what we're doing and everybody does it. Okay? So just because we're not doing a summative doesn't mean that's going to be true for your other courses, just so you know. Okay? Okay. So the product rule. Now the last rule we did was the derivatives of composite functions, or the chain rule. The product rule, when I first taught this course, I would usually teach product rule and then the quotient rule and then the chain rule. But the chain rule comes up more often than I thought it would. All the teachers in the textbook and the teachers at our school will usually teach the chain rule first and then the product and quotient rules. Okay, so um, this rule is actually simpler than the chain rule. And we're going to use examples in here where we're actually using the product rule and the chain rule together. So that's kind of why we did the chain rule first. Okay. Nothing really new in the definitions. When we talk about the product rule, it's basically when you have two functions multiplying with each other. So f of x times g of x creates a new function. So what if we want to take the derivative of that new function? And this is very important here. This doesn't say what it is, if it says what it's not, okay? Because a lot of people think, oh, wouldn't we just take the derivative of the first function times the derivative of the second function? No, that's not how it works. Okay, so what it is, okay, so here's the actual product rule. So the derivative function h prime of x would be the derivative of f times g of x plus f of x times the derivative of g of x. Okay, so hopefully you kind of see the symmetry there. The derivative of one times the other function plus the opposite. Okay, now does it really matter which derivative you take first? No, because the fact that you're adding here, I could switch the order of these two around and I'm going to get the exact same answer. Okay. Um, Now this one here, we've kind of seen this already when we did the chain rule. So if you had g of x to the power n, if f of x was g to the x to the power n, then the derivative of f of x, f prime of x is equal to, and this time we actually, so we're looking at the exponent there. So as part of the chain rule, that comes out in front. You multiply by what g of x was here. That doesn't, the brackets stays the same. You reduce the exponent by 1, and then you multiply by the derivative of what's inside the brackets. Okay, so this is basically the chain rule, but we're just kind of repeating it. We call it the power of a function rule. Okay. In some cases, and we'll see a couple of examples, you might think, well, it seems like a lot of work to do it this way. Couldn't we just multiply the two functions and then treat it as a single, single polynomial functions? Yeah, sure, you could do that. So it depends on what you've been given. It might make more sense, like it says here, to expand and simplify the product before you differentiate rather than use the product rule. So that is an option, and in some cases it might be the better option, but it is it is an option that you could use. Okay, now this is important. If you're taking the derivative at a particular value, so for x equals 3, you don't have to simplify the derivative before you substitute. In fact, it's a lot easier in a lot of cases to not simplify and just plug in the value, okay? But if you're asked to take the derivative of the function for all x, you will have to simplify, and I'll talk about how much you have to simplify when we do some examples. Okay, so here's the product rule. We've already stated this one already, and here's the, if you had u and v, this is more in terms of Leibniz notation. So the derivative with respect to x of u times v, where u and v are functions, is the derivative of u with respect to x times the function v plus u, the function u, times the derivative of v with respect to x, which is really just what we've said above here. We've got u and v instead of f and g, and we're using the Leibniz notation instead of the prime. Okay, so just the two different ways of stating it there. So let's try one. Apply the product rule. We've got h of x equals x squared minus 3x times x to the 5th plus 2. So we can actually treat this, I won't do this every time, but you could say, well, here's my g of x here. Oops. Sorry, here's my f of x, here's my g of x. And just to keep track. So if I'm taking the derivative, h prime of x, okay, it's going to be, again, the order doesn't matter, but I'll go by the book here. It's going to be f prime of x, so the derivative of this. So the derivative of this is 2x minus 3. Make sure that's in brackets because we're going to multiply this. Then we multiply with g of x, so that doesn't change, x to the 5th plus 2. And then we add, so it's going to be the product of f, so that's x squared minus 3x times the derivative of g of x, so that's 5x to the 4th. Okay, I'm not going to spend a lot of time on these derivatives, you should know those. So now, since this is derivative with respect to just x, not for a specific value of x, we're actually going to expand and simplify. So I got a couple of FOILs here. I've got 2x to the 6th plus 4x minus 3x to the 5th minus 6. Okay, so that's that FOIL, and then I've got x squared times 5x to the 4th, so that's 5x to the 6th, and then minus 15x to the 5th. Okay, so we've expanded. Now we can simplify because we've got a couple of several like terms here. So I've got 7x to the 6th from those two. I've got 2 with the 5 here, so that's going to be minus 18 x to the fifth. So that's those two. And then I've just got what's left over here, plus 4x minus 6. All right, so there's our derivative of h. H prime of x is that. Okay. And for this, there's really no decision to be made here. If you're asked to simplify, this is the only acceptable answer. These ones above here would not be accepted. So part marks are big on these derivatives. Obviously, very important to get that first step, but also very important to simplify to whatever level you need to. Okay, so this time we're trying to find the derivative at the value of x equals -1 for the derivative of h, or h prime. And here's here's the definition of the function h of x. Now, I mean, here's a case just like the last case. Maybe we could just expand here. You're actually going to have 9 multiplications. You could do that, and then it just becomes a regular polynomial function, and then you just take the derivative that way, and we don't really have to do the product rule at all. But in this case, let's try it out. I think it's easier to do product rule in this case. So first, we're just going to do h prime of x, and then at some point we're going to sub in -1. So if I'm treating that like my my f of x, and that's my g of x. So take the derivative of this first. So that's going to be 15x squared for the 5x cubed. And this is going to be plus 14x. Then we multiply with the second function, 2x squared plus x plus 6. And then we add the first function, f of x, if you want to call it that, and then times the derivative of the second function, g of x. So that would be 4x plus 1. Okay, so a lot of expanding to do here. Again, I mean, we've already got, this is going to be 6 multiplications, and this is going to be another 6. So it might have been better just to do just to expand it at the beginning and then take the derivative. Okay. Now, since we're only doing a specific value of x for the derivative, meaning for x equals -1, what I was saying earlier at the first page, you don't have to fully expand this and simplify and then substitute in -1. Why not just substitute -1 in now? Be a lot less work. So everywhere I see an x becomes -1. So 5 -1 cubed plus 7 -1 squared plus 3. Running out of room, so that's a 4 times -1 plus 1. Okay, so when I simplify this, that becomes, that's a 15 minus 14, so that's a 1 in the first set of brackets. This would be a 2, 2 plus 1, sorry, 2 minus 1 plus 6, so that's going to be a 7. Then I got my plus sign, and then this set of brackets here, that's going to be a -5. That's going to be a plus 7 and a plus 3. So that's a plus 10 and a minus 5, so that's a 5. And then finally here we got a -4 plus 1, so that's a -3. So now we can just, so it's going to be 7 minus 15, so that's -8, and we're done. So h prime at -1 is, the answer is -8. So like I said, did we need to simplify this and then substitute? No. We can, if it seems like it's going to be more work to do both, just substitute in right away. But if they just ask for h prime of x, we would have to do all the simplifying. Okay. This is an interesting question because we looked at what if you multiply two functions together. how do you take the derivative of that? So in this case, we have this function p of x, which is the product of three different functions, f of x times g of x times h of x. So how would the product rule relate to that? So we can show how it works. What we're going to do first is kind of glue together these two functions. Consider that to be the first function, and that's the second function. Let me straighten that out, move it up. So this is like my first function, that's my second. So when I'm taking the derivative, I first take the derivative of this. So I'm going to take f of x, g of x. That's multiplying. We're taking the derivative of whatever that is, and then multiply with h of x. And then we add, so again, if that's the first function, we take that, so f of x times g of x. We need that bracket there. And then you multiply by the derivative of h, so that's times h prime of x. Okay, so this looks pretty good. Like, this seems like it's all done. This is f times g times the derivative of h, but I got to do a bit of work on here. So this f of x times g of x, if I want to take the derivative of that, well, that's basically the product rule. So this is, if I'm just going to repeat this, it's going to be, so that's going to be f prime of x times g of x. And then the second part of the product rule, f of x times g prime of x, square bracket, and this whole thing is multiplied with h of x. And then I've got this three function product here, f of x, g of x, h prime of x. Okay, so all I'm going to do is take these two products, multiply by this third function. So I've got f prime of x, gx times h of x. So that's the first one. And then f of x plus f of x, g prime of x, h of x, plus this thing here. So f of x, g of x, h, don't need that, f of x, g of x, h prime of x. So this sort of makes sense. I've got three products for the derivative of this three product function. All three of them have an f, a g, and an h, and each one we're taking, one of them is a derivative, right? So in this product, we're taking the derivative of f. This product, we're taking the derivative of g. In this one, we're taking the derivative of h. So you can kind of see where this is going. Like, you could actually figure out, well, what if it was four functions multiplying? Well, then you'd have four separate products. Each product has all four functions, and each product contains one of the derivatives. So that's kind of to basically extend. How could you extend the product rule for a more complex function with more products? So this was a nice way of showing how it works. Okay. So you may get questions like that with maybe three products. Calculate the derivative of a function with three products. Here we're going to use the power of function rule, so the chain rule. Find the derivative of h prime of x. Sorry, find h prime of x. So again, we start by taking the exponent, putting it out front with the coefficient, multiplied by the original base in the brackets. And now we reduce the exponent by 1, so that's now to the fifth. And now we also have to take the derivative of the inside function. Okay, so that's going to be a 2x plus 3. Okay, now you might think, well, I'm done, right? Well, I want you to simplify it a little farther. Okay, I certainly don't expect you to expand that. We're done with this. Okay, but the 6 can multiply with the 2x plus 3. So we can put that out front in brackets. That would be 12x plus 18 times x squared plus 3x plus 5 to the power 5. So I would expect you to go to this, to simplify this far. Okay, this isn't quite enough. If you see some single monomial terms that are multiplying, or a monomial with a binomial, it's not that hard to multiply these together to make this look a little bit more easier to digest. Okay, so that's a good example. How far do we need to simplify? And that's what I'm looking for. Okay, example 5. Determine the derivative of a rational function. And so it says differentiate this rational function by first expressing it as a product and then using a product rule. So we're actually going to do, the next lesson we're going to learn how to do this using the quotient rule. The answer will be the same as if with this technique. So what we want to do here is express it as a product. So really, this is like, we could put brackets here. These are both to the power 1. But I could move that 3x minus 1 up to the top by changing the exponent to be negative. So I can write it like this: 2x plus 5, 3x minus 1 to the negative 1. Okay, and now we can consider this as a product of two functions, not the quotient of two functions, which this really is. Okay, so if I'm taking the derivative of f of x, okay, I'll start with that, 2x plus 5, so f of x now times the derivative of the second function. So remember, this is the exponent. That becomes a multiplier, or part of the coefficient. Then I got the 3x minus 1. Now, the exponent decreases by 1, so that takes it to negative 2. Okay? So that's the first part of the product rule. F of x times the derivative, this times the derivative of this. Now we do the other way. We take the derivative of this. Oh, we're not quite done there, are we? I forgot to take the derivative of this function, so that's a 3. So it looks kind of complicated because of the derivative, taking the derivative of that is complicated. Okay, but we're done. So now we do the second part, which is take the derivative of this function, which is just 2, times the original function here. So that's just 3x minus 1 to the negative 1. Okay, now you can see here we got some binomials to negative exponents. Well, that we're going to have to change the way that looks. So I'm going to have two rational expressions. So the first one is from here, the 3x minus 1 to the negative 2. That becomes 3x minus 1 squared here. So I brought that down there, and then the top is just the product of these three. So that's basically negative 3 times 2x minus 5, which is negative 6x minus 15. So that's what this reduces or simplifies to this. And then this one here, this negative 1 means I just bring it below here. Exponent would be 1 from negative 1. And then on the top we just have a 2. Sorry, is that right? Yeah. Okay, now you may say, okay, that looks like we're done, but we're not. Okay, and this, you can see here I've got a 3x minus 1 to a power 3x minus 1. Well, all I have to do here is I'm going to multiply the second expression by 3x minus 1 over 3x minus 1. And what that's going to do is create the same denominator over here as we have here. So when we do that, negative 6x minus 15, 3x minus 1 squared, plus, now on the bottom we got 3x minus 1 squared, On the top now we have 2 times this, so that's going to be 6x minus 2. Okay, so now we can combine these two rational expressions. We now have 3x minus 1 squared on the bottom, and then we just combine these two. So negative 6x plus 6x, that cancels out. Then I have negative 15 minus 2, that's negative 17, and that is fully simplified. I'll put this back out front again. Okay, so you can see how much more simplified that looks compared with what we thought we should leave it at maybe. So that's when you're doing anything with a rational function, you're going to end up usually with a single term, with a single expression here. Okay. Now, when we learn the quotient rule, you'll see how we'll get the same thing by doing a different technique. And we can talk about that on the next lesson. Okay. All right. Here's a word problem. The position in centimeters of an object moving in a straight line is given by s. So s is the position. Is equal to t times 6 minus 3t to the fourth. T is greater than 0. T is the time in seconds. Determine the object's velocity at t equals 2. So the first thing you have to understand is to get the velocity of this object. If I have the equation for the position, if I do the instantaneous rate of change of the position, that gives me the velocity. So what I'm looking to do is I want a new function which is velocity given time. Now that's really the same thing as s prime. Okay, I could put s prime of t. So the velocity is the rate of change of the position. Okay, so what I need to do is take the derivative of this function s. So again, this is a product, right? I've got the t in front is like its own function, and then the 6 minus 3t to the fourth, that's the second function. So when I take the derivative of that, okay, derivative of t with respect to t is 1 times 6 minus 3t to the fourth. Okay, and then we add the first function, which is just t. Might as well put that in brackets. And then times the derivative of 6 minus 3t to the fourth. So that 4 comes out in front. It's a multiplier. Then I have 6 minus 3t. And the exponent is reduced to 3. And then we take the derivative of what's inside here, and that's going to be minus 3. So let's simplify this. So v of t, so that 1 doesn't really do much, so it's just 6 minus 3t to the fourth. And now here we have to multiply these three monomials together. So negative 3 times 4, negative 12t goes out in front, and then 6 minus 3t cubed. Okay, so that's pretty simplified. You might think, well, couldn't we factor out this? Well, you could, but it's not really. Simplifying should be the opposite of factoring. So in this case, let's just leave it. We're just going to leave it the way it is. Okay. Now, what we want to know is we want the object's velocity at t equals 2. So that's v at 2. So in this case, t is equal to 2. So this one is actually pretty quick, because if I plug in a 2 here, 6 minus 3 times 2 is 0. 0 to the power anything is 0. Here I've got, well, that's going to be like negative 24. But this thing is also going to be 0. 6 minus 3 times 2. So we have 0 minus 0. So the velocity at 2 seconds is 0. So in terms of velocity, the speed is 0, the direction is 0, the object is stopped. Object is stopped at t equals 2. Okay, so that's, you had to kind of figure out what does velocity have to do with position. Well, hopefully you understand that velocity is the derivative of the position function. Okay. All right, so that was some examples of using the product rule. If you want to try some of the questions down here, make sure you're able to do this. I'll post the solutions along with this lesson. And the next lesson, which will be posted Wednesday morning, will be on the quotient rule. And then the final lesson of the week will be on second derivatives. Okay, and then we'll move on next week to curve sketching. Okay, thanks guys, have a good day.